We have Newton's first law of motion, which tells us what to expect for an object when the sum of the forces is zero. We have Newton's second law of motion, which tells us what to expect when the sum of the forces is not zero. And now we're going to learn about a few specific forces, enough to get running with things. Obviously, there's more details than fit on this one slide. This is a first pass at a few specific types of forces, and we'll learn about these in more detail as the course unfolds, and learn about some other forces as time goes on, things like the buoyant force or an air drag force or other sorts of things. All right, so first we have weight. This is the pull of Earth's gravity on everything that has mass. It has the following characteristics. The direction of weight is going to be straight down to the center of the Earth, and the magnitude of the weight vector is mg. M is the mass of the object in kilograms, and g is the acceleration due to Earth's gravity in meters per second squared. If you're taking the average value for the surface of the Earth, that's 9.8 or 9.81 if you need an extra significant digit, meters per second squared. Later on in the course, I actually have a lab and you'll measure that for yourself. It's not too hard to do with a pendulum. All right. I also want to emphasize that weight is a force. We'll measure it in newtons and MKS. Mass is not a force. It's a scalar. It just has a value, and we will measure that in kilograms in our MKS system. All right. The next two categories of forces go together. These are contact forces. So when I have two objects in contact with each other, like I set my coffee cup down on my desk, which I do quite frequently, the coffee cup does not fall through the desk. My desk prevents that from happening by exerting a normal force. And normal, I want to emphasize, means perpendicular direction. It's that sense of the word normal, not like in contrast to abnormal or supernormal. Normal force, I have a contact between two objects. They are in contact with each other, whatever the orientation is. The perpendicular component of contact force between those two objects is the normal force. The side to side, so if I try to slide one hand past the other, that takes some effort because there's friction. So friction is the parallel component of the contact force between those two objects in contact. Friction is its entire field of study. It's a very important field of study. It's tribology. The level that we're going to deal with things involving friction, we're going to have a couple of relations for static friction. So that's what you'll observe when the two objects in contact are not moving relative to each other. And then there's also kinetic friction. So if one is sliding past the other and there's relative motion at that interface, then that is kinetic friction. But the next chapter is going to have some more details on friction, and then the entire subject of friction is its own study. Lastly, is the force of tension. Not lastly in the sense that this is the only force we need, but this is the last force in this first pass at forces. Basically, I tie a string on something and I pull. That pulling force is transmitted along my string from where I'm holding it with my hand and pulling to the object that I tied it off to. So tension is a way of representing that I am exerting a force by attaching this material object like a string or a chain or a cord or something that allows me to exert a pull along the direction of that string. So a few things to mention. Number one, a string, I can tie a string onto an object and pull. I cannot push. A string cannot push. So whenever you're drawing out free body diagrams or thinking about equilibrium or doing things with tension, try to keep in the back of your mind, a string can only pull. A string cannot push. So it'll help you with your direction of the force of tension. Uh, Force of tension at the level that we're going to mostly deal with it, we're going to have a cord that has no mass, so it doesn't have to support its own weight. If I do have a situation where the weight of the cord or cable or chain or whatever is not negligible, then I'm going to have a differential equation to solve for what's the equilibrium shape. And if you look at the shape of a telephone wire that's hung between two poles, it sort of has that gentle upward curve shape. It's called a quaternary, and it's one of the classic first applications of ordinary differential equations, is to find the equilibrium shape of a uniform density string that's supporting its own weight. It's a unneeded complication for what we're doing with physics at this level. It doesn't bring any more physics to light. So unless otherwise stated, we're just going to assume that our chords and strings and whatever are massless, or at least their mass is insignificant compared to the force of tension within them. All right. Another thing I want to mention, weight, we have a formula for. Friction, we will have some relationships for, but they're not necessarily an equality. The force of static friction is actually an inequality. It has to be less than or equal to some value. The normal force, it's not an equation for it. You will find the normal force from either equilibrium or the motion of an object. And similarly with tension, there's not an equation to look up in the book for tension. Tension is going to come from your free body diagram and applying Newton's first or second law as appropriate. The tension will take the value that it needs to have for equilibrium, or the tension in the rope will take the value that it needs to have for a ball to swing around in a circle. There's not a fixed equation for tension. Tension is what it needs to be to explain the physics that you see. All right, I have some questions to try to help you not get stuck on some of the popular misconceptions with these forces. And I'm going to spend a little bit of time thinking about tension. So for this first question, some children are pulling on a rope that is raising a bucket by a pulley up to their treehouse. The bucket containing their lunch is rising at a constant velocity, ignoring the mass of the rope, but not ignoring air resistance. Which one of the following statements concerning the tension in the rope is true? So read through those choices, see which one makes sense in terms of Newton's first law, Newton's second law, and what we know about forces now. And then talk that over with your physics friends. And when you're ready to continue with the answer, unpause the video. All right, so some keywords here. The bucket containing their lunch is rising at a constant velocity. So we know from Newton's first law of motion, if the velocity of an object is constant, that means that the sum of the forces on the object is zero. So that applies to our lunch bucket that's going up to the treehouse. And that is the object's velocity is constant if and only if the sum of the forces is zero. So we have the weight of the lunch bucket is going to act straight down. It is moving up, so air resistance also acts down. And so the force of tension has to be enough to cancel out both the weight of the lunch bucket and the force of air resistance on it. And that's how we can get to the sum of the forces is 0, and it rises at a constant velocity. All right, that was kind of a warm up. Let's try a harder question. And this next question, really got to make sure it makes sense to you. We have two identical cement cylinders attached to the opposite ends of a spring scale via very light ropes. So the mass of the ropes can be neglected. They run over frictionless pulleys, which just redirect the force. When the same scale was suspended from the ceiling and one of the cylinders was hung from it, the scale indicated its weight is W newtons. What would the scale read in the configuration shown? So now the spring scale is horizontal and I have weights hanging off on both sides. So think about it, talk about it with your physics friends. If you're stuck and you don't know how to proceed, imagine a free body diagram for the spring scale. It's a great place to start, because everything in the system, the cement block, the rope, every section of the rope, the spring scale, all the way through to the other cement block, all of those objects begin and remain at rest. And that tells you something very important. So think through what you think the answer is, talk it over with your physics friends, and then unpause the video and we'll go over the answer together. All right. This usually surprises people at first. It's going to read the same thing. Scale is going to read a weight of W newtons, whether the scale was hung vertically and there's one cement cylinder hung off of it, or in this arrangement, it's hung horizontally and there's two, one cement cylinder pulling from one side, one cement cylinder pulling from the other side. All right. So here's what we need to think about for this answer to make sense. So this cylinder on the left has some weight. Okay. That means its weight is canceled out by tension in the cord. So the tension in the cord is W in magnitude. And every little segment of this rope is being pulled by a force W to the right and W to the left, or W up and W down, depending on where you're at relative to the pulley. And that makes every little piece of the cord in equilibrium. I can do the same analysis from the right cement cylinder. It has a weight W, but it begins and remains at rest. So it's pulled up by a tension that is W newtons strong. And I keep on, every little segment of the rope is being pulled by a tension above and below, or a tension right, left, of magnitude T all throughout the rope until I get to no more rope. So now I look at the spring scale. The spring scale is being pulled to the left with a force of magnitude W arising from tension, and the hook on the spring scale is being pulled to the right by a force of tension of magnitude W. And this is precisely the same arrangement in which if it was hung vertically, the scale reads W, right? I'm hanging the scale, so there's a force of magnitude W tension in the cord below the scale. But there are also, if I'm hanging it from the ceiling, right, there's also a force of magnitude W all throughout the cord above the spring scale. So this is what it means to read a force of W. The spring scale is in equilibrium and it's being pulled by a force of magnitude W in both directions. All right. And Newton's first law obviously is crucial in that analysis of the tension. Very important idea. All right. So another example would consider a person standing in an elevator. That elevator is accelerating upward. The upward normal force N exerted by the elevator floor on the person is it larger than the downward weight, identical to the downward weight, or smaller than the downward weight of the person? So try to think of a free body diagram for a person in the elevator, and the elevator is accelerating upwards. Which of those three is correct. Talk it over with your physics friends, and then when you're done, let's go over the answer. All right. To accelerate upward, the normal force has to be stronger than the weight of the person. The person is going to accelerate along with the elevator. They're not going to fall through the floor. At least I hope not. And so the floor is providing a larger force. So it cancels out the weight of the person and provides enough extra force for the person to accelerate along with the elevator. And this is why, if you've ridden in an elevator, there are times when it's really easy to jump up because the elevator is accelerating down. So the floor is partly falling out from underneath you, and the normal force exerted on you is less than your weight. So you can make a better jump. And then sometimes it's harder to jump up in an elevator, as in this case, when you're accelerating upwards, because the floor is already accelerating up along underneath your feet and pushing you. If you think about those cases, you will sometimes feel heavier than your weight, and you'll sometimes feel lighter than your weight when you're in an accelerating elevator, which can be fun. Another thing to mention about this upward normal force, that is the same idea as what a scale is going to read for your weight. If you think about that, the scale doesn't actually know the force of gravity that Earth exerts on you. What it does know is how hard your feet are pushing down on the scale. Okay. If you're not accelerating, then you are going to push down on the scale with as much force as your weight. But let's say I hand you a 10 kilogram cement block. Is the scale going to read your weight anymore? No, it's going to read your weight plus the weight of that 10 kilogram block. The scale doesn't know anything. It just knows the contact force that you're applying to it. All right.